Good day. Today we'll discuss statistical analysis made simple. And these are the learning objectives for today's session that at the end you'd be able to discuss and understand the principles behind statistical tests. And then identify what statistical tests to use given a particular specific objective. And this will be the outline of today's lecture. We'll be talking of the principles behind statistical tests, and then identifying statistical tests, and lastly, we'll give you some examples and exercises. Now, let's begin with the principles behind statistical tests. You see, class, when we want to look into the relationship between an independent variable and a dependent variable, we normally do statistical tests using a univariate analysis. Univariate analysis means looking at one independent variable and one dependent variable one at a time without looking into other factors that can affect the relationship. Now, if we want to look for other factors that can affect the relationship, we need to do a multivariate analysis. So again, a univariate analysis is looking at one independent and one dependent variable in the relationship without considering other variables that can affect the relationship. And multivariate analysis looks into many independent variables and one dependent variable. Let's give an example. Suppose the objective of the study is to determine the relationship between height and cardiovascular disease, height being the independent variable and cardiovascular disease the dependent variable. Now, to answer that objective, a univariate analysis will need to be done initially. And we said that univariate analysis is looking at one independent variable, in this particular example, height, and one dependent variable, cardiovascular disease. And we don't consider other variables that can affect the relationship. But we know that there are other factors that can affect cardiovascular disease, the outcome. For example, smoking status, systolic blood pressure, history of diabetes, BMI, body mass index, lipid markers, alcohol consumption, educational level, and occupation, among others, are factors that can also affect cardiovascular disease. Now, to determine the exact relationship between height, the independent variable, and cardiovascular disease, the dependent variable, all these other factors that we have mentioned a while ago need to be controlled. And control of these other factors will be done using multivariate analysis. Now, let's give another example to determine the predictors of myocarditis among patients with dengue hemorrhagic fever. Now, the difference with this objective from the previous objective that we gave you is that in this particular objective, we have already many independent variables, predictors. These are the independent variables, and we can have many predictors of myocarditis being the dependent variable. A while ago, we just had in our relationship, example of the relationship between height and cardiovascular disease, we only had one main independent variable, height. all other variables were considered as confounders. Now, in this particular example now, when we talk of predictors, we have many independent variables and one dependent variable. Now, to answer that objective, a univariate analysis will be done initially. Each of the identified predictors, because we told you we have many predictors, each of these predictors will have to be analyzed in the univariate analysis, one predictor at a time. One predictor at a time. That's a univariate analysis. Now, a multivariate analysis will then be done after doing univariate analysis. Now, all variables identified in the univariate analysis that could be seen as possible predictors of myocarditis will have to be analyzed in the multivariate analysis, this time all variables analyzed simultaneously. Because a while ago, with univariate analysis, though we have many independent variables, we analyzed these independent variables one at a time. So that's still univariate analysis. But with multivariate analysis, we analyze all variables simultaneously. That's multivariate analysis. So that basically, class, is the principles behind statistical analysis. Now, let's go to the next topic, identifying what statistical tests to use given the objectives of the study. Now, the statistical test to use in a study really depends on two important information: the data classification and the type of the variables, the type of relationship of the variables. Now, different data classifications entail different statistical tests. We'll talk first of the different data classification. We told you last time when we talked about data classification that data can either be qualitative or quantitative. And just to give you some review examples of qualitative data, exposure or risk status like smoking status. So either a patient is or a participant is a smoker or a non-smoker. Disease status, either a participant has dyslipidemia or without dyslipidemia. Physical activity, another qualitative data classified as either sedentary or active. Now, examples of quantitative data: AIDS in years, platelet count, blood lead levels in micrograms per deciliter, fasting blood glucose, and cholesterol levels. These are quantitative variables. Now, we also have what we call the scale of measurement. And we have discussed this to you last time, so we'll just identify them: the nominal, the ordinal, the interval, and the ratio. Now, nominal and ordinal scales of measurement can be seen as qualitative data, and interval and ratio scale measurements can be seen as quantitative data. Now, let's talk of relationship among variables. In the relationship between variables, we have the independent variable, that's also known as the determinant or the predictor variable, and a dependent variable, that's also known as the outcome or the response variable. And the independent variable is presumed to cause, affect, influence, stimulate, or predict an outcome. The outcome, the dependent variable. And the dependent variable is the result or the outcome in its relationship with the independent variable. Now, many times it's easy to tell what is the dependent variable and what is the independent variable. For example, lung cancer and smoking, we know right away what is the dependent and what is the independent variable. So we know that lung cancer is the dependent variable and smoking is the independent variable. At other times, however, we need to know the objective of the study to determine what is the dependent and what is the independent variable. For example, malnutrition and measles. Here, either measles or malnutrition can assume as either dependent or independent variable, really depending on the objective of the study. If the objective of the study is determining factors related to severity of measles, then malnutrition is the independent variable, meaning if you are malnourished, you're more likely to have severe measles. If, on the other hand, the objective of the study is determining factors associated with malnutrition, then we know that malnutrition now becomes the dependent variable. If you get measles, then you're more likely to develop malnutrition. Now, with statistical tests, we need to understand as well that there is such a thing as what we call parametric tests and non-parametric tests. Parametric tests involve specific probability distributions, meaning outcomes have to be normally distributed, and estimation of key parameters of that distribution. For example, the mean or the difference in mean from sample data. And parametric test is used when the variables are measured in the ratio scale. Now, parametric tests, on the other hand, are sometimes called distribution-free tests because they are based on fewer assumptions. That is, they do not assume that the outcome is approximately normally distributed. Now, let's talk first of descriptive statistics. We don't have here hypothesis testing. We're just talking of descriptive statistics, estimation, for example, estimating a parameter. And if we want to estimate a parameter that's qualitative in nature, and then the statistical test will just be a frequency and percentage. And then the 95% confidence interval of the proportion or frequency can also be calculated. Accuracy of a test using sensitivity and specificity falls under descriptive statistics. Now, if we are trying to estimate a population mean for quantitative data, for example, and then we talk of the mean and the standard deviation. And then we can also calculate the 95% confidence interval of the mean. Now, let's go to test of hypothesis. If we are testing hypothesis, if we are testing relationship. So this is the basic principle that I want you to memorize. Well, it's not really difficult to memorize this one, but this forms the basis of, or the basic principle in statistical tests. Now, if both the independent and the dependent variables are qualitative, the statistical test to use is a chi-square test. Odds ratio, prevalence ratio, and risk ratio may also be used to test the association for a 2x2 table. Now, if the independent variable is qualitative and the dependent variable is quantitative, then t-test for two means may be used interchangeably with ANOVA. But if there are more than two means to be compared or tested, then ANOVA will be the only choice. Later on, we'll give examples. Now, if the independent variable is quantitative and the dependent variable is qualitative, then simple logistic regression is used. And lastly, if both the independent and the dependent variables are quantitative, then simple linear regression is used. We can also use Pearson's correlation coefficient. Now, this table should come handy. It should tell us what statistical tests to use given the different data classification for the independent and the dependent variables. So just to summarize, if both the independent and the dependent variables are qualitative, then the statistical test to use is chi-square test. The prevalence ratio, the risk ratio, or the odds ratio can also be used. Now, if both the independent variables and the dependent variable are quantitative, then linear regression is used. Now, if the independent variable is qualitative, the dependent is quantitative, then t-test or ANOVA can be used. And then if the independent is quantitative and the dependent is qualitative, then logistic regression is used. Now, let's give examples for each of these tests. So, both qualitative, independent, and dependent variables. And we told you that the statistical test to use is a chi-square test, and then prevalence ratio, odds ratio, and risk ratio can also be used. Now, prevalence ratio, we told you, is used for a cross-sectional study, and risk ratio for a cohort study, and odds ratio can be used for a case control study. But mind you, that odds ratio can also be used in a prevalence study, in a cross-sectional study, or in a cohort study. We actually discussed this to you when we discussed research design. Now, let's give an example for the chi-square test. The objective is to determine whether levels of snoring behavior is associated with heart disease. In this particular objective, the independent variable is heart disease and the dependent variable is level of snoring behavior. So both are qualitative in nature, so the statistical test to use is a chi-square test. Now, if data come from a cross-sectional study or a cohort study, then prevalence ratio or a risk ratio is used. We said that to you a while ago. And then if data come from a case control study, odds ratio is used. And I would like to emphasize that in a case control study, the only measure is odds ratio, meaning we cannot measure the prevalence ratio or the risk ratio in a case control study. Now, if the independent variable is qualitative and the dependent variable is quantitative, the statistical test to use is a t-test or ANOVA. Let's give an example to determine the relationship between high school grade and sleep-wake schedules. Sleep-wake schedule was measured as less than 6 hours of sleep and 6 hours or more, and high school grade was measured as average grade in percent. In this particular objective, the independent variable is sleep-wake schedule, as we said, measured as less than 6 hours and 6 hours or more of sleep, and that's a qualitative independent variable. And high school grade was measured as average grade in percent, and that's the dependent variable measured quantitatively. And so the statistical test here is a t-test. So actually, ANOVA can also be used, but the more appropriate statistical test will be a t-test when there are only two means. So two means, so one mean for those mean grade for those sleeping less than 6 hours, and another mean for those mean grade for those sleeping for 6 hours or more. So t-test. Now, if there are more than two means to be compared, then ANOVA will be the only choice. We cannot use a t-test when there are more than two means to be compared. And so, for example, if sleep-wake schedule was measured as less than 6 hours, 6 to 8 hours, and more than 8 hours, so we have three categories for the independent variable, and then the statistical test to use is ANOVA. Now, just would like to mention that there is such a thing as a paired t-test. Paired t-test is used when you compare two means for measurements done twice for the same sets of participants. A while ago, we talked about the t-test. That's also called an independent t-test or a student t-test. It is called an independent t-test because the two means being compared are independent of each other. In a paired t-test, we are actually talking of the same participants, same sets of participants, but you measure them twice. So there is a before and after procedure or treatment test. So for example, we want to look into whether swimming can increase PEFR among asthmatics. PEFR is peak expiratory flow rate, and a pre-swimming peak expiratory flow rate is taken. And then the participants is asked to swim for about 30 minutes, and then after swimming for about 30 minutes, a post-swimming PEFR will again be taken. So there are two means, the pre-swimming PEFR and the post-swimming PEFR. So if we are comparing two means for the same sets of participants, and then a paired t-test will be the statistical test. Now, when we want to compare means measured more than twice, and then the statistical test is a repeated measures ANOVA. For example, if you want to look into whether a special form of exercise will reduce the BMI of obese patients, so you get a BMI measurement at baseline, and then you do the exercise, you make people exercise a special form of exercise, and then 1 month after the exercise, the intervention, you again measure the BMI, and then measure it 3 months, 6 months, and 12 months later after the exercise, because we have more than two measurements. So we measure more than two means, and then you're talking of the same sets of participants. The statistical test to use is a repeated measures ANOVA. Now, we have quantitative independent and dependent variables. Both independent and dependent variables are quantitative, and the statistical test to use is a linear regression or a Pearson's correlation coefficient. So we want to look into the relationship between birth weight of babies. This is your dependent variable, and that's quantitative, and the age of the mother, quantitative independent variable. So both dependent and independent variables are quantitative, and the statistical test to use is a linear regression. And linear regression many times can be depicted in a plot called a scatter plot, and that scatter plot can be summarized by a line, and if the line is going up, and then that's the slope of the line is going up, and then we say that the relationship between the independent, normally in a scatter plot that's denoted by an x by the y-axis, the dependent variable, and the independent variable by the x-axis. And if the line is going up, it says that as x increases, or as the independent variable increases, so does y, so does the dependent variable. Now, if the line is going down, the slope of the line is going down, we say that as x increases, y decreases. And if the line is a horizontal line, and then when x increases, y does not change. So in the first, when the line is going up, we say that there is a relationship between the independent and the dependent variable, and the relationship is a direct relationship. But in the second, when the line is going down, the slope of the line is going down, we say that the relationship between the independent and the dependent variable is inverse. But when the slope of the line is horizontal, we say that there is no relationship between the independent and the dependent variable. Now, the last is when we have a qualitative dependent variable and a quantitative independent variable, and then logistic regression is used. And this is closely related to the odds ratio. The difference is that here we deal with quantitative independent variables. So let's give an example to determine the relationship between BMI and osteoporosis. And BMI is the independent variable, and that's quantitative. And the dependent variable is osteoporosis, that's qualitative, and so logistic regression is used. As a matter of fact, odds ratio can also be calculated, and when we calculate odds ratio where the independent variable is quantitative, we talk of a unit increase in the independent variable, and then odds of, then we talk of the odds, whether it is increasing or decreasing for the dependent variable. Now, let's talk of non-parametric tests. As we said, non-parametric tests are used when variables are not normally distributed, and variables are measured in the nominal, ordinal, or interval scales. And again, this should come handy for non-parametric tests. We have here in the first column the independent variable, in the second column the dependent variable, and then the statistical test for the last column. And I would like to emphasize to you that in non-parametric tests, all independent variables are qualitative, and what varies are the dependent variables. So if we have an independent variable with two categories that are independent of each other, so meaning these two categories are independent. So for example, a smoker, smoking status, smoker and non-smoker, they are independent of each other. And then the dependent variable has nominal scale of measurement that's also qualitative, and the statistical test to use is a chi-square test, because we told you that chi-square we have both qualitative for independent and dependent variables. And then we can also use the Fisher's exact test if the sample size is much too low. Now, if we have two categories for the independent variable, but they are matched or related, they are paired, matched or related, meaning they are measured, they have they are one same participants, you measure them twice. And then the dependent variable is nominal. The statistical test to use is a Mach-Neymark chains test. We'll give an example of a Mach-Neymark chains test. Suppose you want to look into the level of self-esteem before and after a counseling session. So you get the level of self-esteem before a counseling session, and the level of self-esteem is measured as either high or low, that's nominal, and then you do a counseling session, and then you get again the level of self-esteem after that counseling session. You are talking of the same sets of participants, and so the statistical test is a Mach-Neymark chains test. Now, when we have an independent variable with k categories, k means more than 2 categories, and they are independent. So, for example, smoking status, smoker, non-smoker, and previous smoker. So, more than 2 categories. And then, the dependent variable is nominal. Statistical test to use is a chi-square test, because, as we said, chi-square test, we have both independent and dependent variables being qualitative. Nominal is qualitative. Now, if we have k categories but they are matched or related, meaning you are talking of the same sets of participants but you measure them more than twice. So k categories, more than 2 categories, and then the dependent variable is nominal. The statistical test to use is a Cochran Q test. We'll give an example of a Cochran Q test. Level of self-esteem before a counseling session. So again, we have this level of self-esteem measured as high or low, and then that's nominal. And then so we do a counseling session after doing the level of self-esteem, after measuring the level of self-esteem before a counseling session. Then we do a counseling session, and then after that first counseling session, we measure again the level of self-esteem, and then we do another counseling session. After a second counseling session, we measure again the level of self-esteem, and then we make a third counseling session, and then after the third counseling session, we measure again the level of self-esteem. So you will note that we have many, not just 2, but many measurements, more than 2 measurements for the level of self-esteem, and so the statistical test to use is a Cochran Q test. Now, if we have 2 categories, again, independent variable, independent samples, they are independent, and then the dependent variable is now ordinal, no longer nominal, it's now ordinal, and then the statistical test to use is a Mann-Whitney U test. And if this dependent variable, just to review, if this independent variable is a ratio, the statistical test will be an independent t-test. So you will note that Mann-Whitney U test is the counterpart of an independent t-test in a parametric test. Now, if we have 2 categories, meaning you are talking of the same sets of participants, you measure them twice, and then the dependent variable is ordinal, and then we have the statistical test to use is a Wilcoxon Signed ranks test. And if the dependent variable is quantitative ratio, and then the statistical test to use is a paired t-test. So that Wilcoxon Signed ranks test is the counterpart of a paired t-test in the parametric tests. But just to tell you that the dependent variable can either be ordinal or interval, and we have this statistical test, Mann-Whitney U test for 2 categories for independent samples, and Wilcoxon Signed ranks test for 2 categories matched related. We'll give examples of this. Now, as we told you a while ago, the counterpart of t-test. Mann-Whitney U-test is the counterpart of t-test in a parametric test. And as an example, we talk of comparison of pain scale from 0 to 10. 0 to 10 is an interval scale using drug A and drug B. These are independent samples. People taking drug A versus people taking drug B, they are independent of each other. Then we compare the pain scale of these people, and then we use the Mann-Whitney U-test. Now, an example of a Wilcoxon Signed ranks test. As we told you, Wilcoxon Signed ranks test is the counterpart of a paired t-test in a parametric test. So, for example, if we are talking of comparing pain scale from 0 to 10 before and after an intervention, so you're talking of the same sets of participants, you measure the pain scale before an intervention, you give an intervention, and then after an intervention, you measure the pain scale again, and that's Wilcoxon Signed ranks test. Now, independent variable, we have K categories. They are independent samples, meaning they are independent of each other. And the dependent variable is ordinal or interval, and then the statistical test to use is Kruskal Wallis. Now, if this dependent variable is a ratio scale measurement, and then the statistical test to use is ANOVA. So Kruskal Wallis is the counterpart of ANOVA in a parametric test, in a non-parametric test. And if we have K categories but they are matched, meaning they are measured more than twice, and then the dependent variable is ordinal or interval, and then the statistical test to use is Freidman's test. And if this one, the dependent variable is a ratio scale measurement, and then the statistical test is a repeated measures ANOVA, if you can recall. And Freidman's test is a counterpart of ANOVA in a non-parametric test. So, as we told you, Kruskal Wallis is the counterpart of ANOVA in a non-parametric test. And as an example, we are talking of three groups of people using drug A, drug B, and drug C. They are independent of each other, and then you compare the pain scale from 0 to 10. So you use Kruskal Wallis. Now, Freidman, as we told you, is the counterpart of repeated measures ANOVA in a non-parametric test. So we want to determine whether type of music affects perceived effort to exercise. Now, let's try to describe to you how this is done. Suppose you have 10 participants and you ask them to run on a treadmill for 30 minutes for 3 consecutive days. In a random order for 3 days, one subject runs day 1 listening to no music, day 2 listening to classical music, day 3 listening to dance music. Another individual runs on day 1 listening to classical music, day 2 to dance music, day 3 to no music. Still another individual runs day 1 listening to dance music, day 2 to no music, day 3 to classical music, and so on and so forth in a random order. But all 10 participants will need to listen to each of these types of music. And then at the end of each run, subjects are asked to record how hard running session felt on a scale of 1 to 10, with 1 being easy and 10 extremely hard. And then you select all those who ran, the scores for those who ran on with no music, and those who ran with classical music, and those who ran with dance music. You combine all those, and then you look into the difference. And because we are talking of the same sets of participants, and they are measured more than once, more than twice, I should say, and then the statistical test is a Freidman's test. Now, let's talk of measures of association. When we have the independent variable and the dependent variable to be both nominal, and then the measure of association is a kappa coefficient or a Kramer coefficient. If both are ordinal or interval, the Spearman rank correlation or the Kendall-Tau rank order coefficient. And then lastly, if both are quantitative ratio, and then the Pearson's correlation coefficient can be used. Now, let's discuss other tests very quickly. To determine a cut-off value to make a diagnosis of the disease, or to make a prediction, to predict an outcome, a receiver operating characteristic curve is used. Have you ever wondered why? How do people make the cut-off value for a disease? For example, diabetes mellitus. The cut-off value for DM, diabetes mellitus, is 126 FBS, fasting blood glucose. Now, how do they come up with this cut-off value of 126? They calculated the cut-off value using actually the receiver operating characteristic curve, or the ROC curve. Now, for survival analysis, there is time to an event, Kaplan-Meier, or a Cox regression is used. If we want to Kaplan-Meier, if we use it for if there is no control variables, and if we want to control for other variables, we use a Cox regression. In clinical trials, we calculate for the risk ratio, the absolute risk reduction, relative risk reduction, number needed to treat, and then number needed to harm. We discussed this to you when we discussed research design. Now, when the outcome, the dependent variable, is a count within a given period of time, for example, number of people developing a disease after an exposure to a risk factor, the outcome is a count, and then the statistical test to use is a Poisson regression. Now, let's give you some tips when you make your research proposal. For each objective, you identify the statistical test to use. And the data classification, we told you that statistical test to use depends on two important information: the data classification and the relationship among variables. And the data classification and the relationship can be seen from the objectives of the study. So you look at the objective, you look into what is the dependent and what is the independent variable, and then look at the operational definition of each variable, and they will tell us the classification of data. From the operational definition of the independent and the dependent variables, we will be able to know what statistical test to use. And then sample size calculation must be consistent with the objectives of the study. And then the statistical test must be consistent with the objectives of the study and the sample size calculation. And lastly, the dummy tables must be consistent with the objectives and the statistical tests. Now, just to summarize to you, all five have to be consistent. The objective of the study first, and then second, the operational definition, third, the sample size calculation, fourth, statistical analysis, and lastly, the dummy tables. All of these five should be consistent. They should be consistent in terms of data classification, statistical analysis, sample size calculation, and dummy tables. Let's give an example. Suppose the objective of the study is to determine the relationship of interpregnancy interval and risk for infant mortality. From this objective, we can see that the independent variable is interpregnancy interval, and the risk for infant mortality is the dependent variable. Now, we look at the operational definition for us to know the data classification of the independent and the dependent variables. So, as we said, the independent variable is interpregnancy interval defined as time between the last live birth and the date of conception for the current live birth. And this is quantitative, but it was dichotomized to less than 18 months, and then we call it short interval, and 18 months and above, appropriate interval. Because with dichotomized interpregnancy interval, we now know that interpregnancy interval is a qualitative variable. Now, the dependent variable is risk for infant mortality, and it is defined in terms of time of delivery, birth weight, and infant's gestational age. It will be classified as having risk or not having risk for infant mortality, because the risk for infant mortality is classified as having risk or not having risk for infant mortality. We know that risk for infant mortality is also a qualitative variable. And so we have both independent and dependent variables being qualitative, and we know right away that statistical test to use is a chi-square test. Now, but we need to define the independent variable having risk for infant mortality. We haven't defined that yet. So we need to define it operationally. So having risk for infant mortality is defined as anyone or a combination of preterm delivery, meaning below 37 weeks of gestation, low birth weight, less than 2,500 grams, and small for gestational age infants at or below the 10th percentile in birth weight compared to infants of the same sex and gestational age. So anyone or a combination of these three, and then we say that the infant is having risk for infant mortality. Now, not having risk for infant mortality is defined as term pregnancy, that's normal, at or after 37 weeks, normal birth weight greater than 2,500, appropriate is also normal for gestational age infants above the 10th percentile. And so if everything is normal for the three parameters, and then we say that the infant is not having risk or does not have risk for infant mortality. Now, let's look at the sample size calculation. Sample size was calculated based on the comparison of the incidence of risk for infant mortality among mothers with short and with appropriate interpregnancy interval. So this is actually consistent with the objective of the study, looking into the relationship between interpregnancy interval, classified as either appropriate or short, and the incidence of risk for infant mortality. So this is the basis for the sample size calculation. Assuming that among mothers with short interpregnancy interval, incidence of risk for infant mortality is 46.8, and among those with appropriate interpregnancy interval, 37.1, and then we normally say who the author is, where did you get these values, and then with an alpha error of 5%, power of 80%, and a one-tailed alternative hypothesis, sample size calculated is 318 per group or 636 for two groups. We actually gave you a lecture on how to calculate with the sample size, so you don't have to, you need to understand where I got these values based on the discussion, my discussion with you on sample size calculation. Now, controlling for 5 more variables in the analysis with an additional 20% for each control variable, the final sample size is 1,272. So you will note that in the sample size calculation, we controlled for other variables, 5 more variables. And so if we look at statistical test, we say it is the write-up of the statistical analysis to determine the relationship between inter-pregnancy interval and risk for infant mortality. Chi-square test will be used. An odds ratio, a 95% confidence interval, will also be calculated. Control variables will also be examined for their relationship with the risk for infant mortality, initially in the univariate, using univariate analysis, chi-square test, and logistic regression for qualitative and quantitative independent variables respectively will be used. So if the independent variable is qualitative, we use chi-square test, but if the independent variable is quantitative, in the univariate analysis we use logistic regression. And then a multivariate analysis will then be done using multiple logistic regression. Level of significance will be set at alpha equals 0.05. So that's how statistical test is written. And then we look at the dummy table. The dummy table looks into the relationship between inter-pregnancy interval, classified as either short or appropriate, and having risk for infant mortality, number and percent. And then the p-value here, and then the estimate odds ratio, and then the 95% confidence interval. And then we placed here an asterisk saying that the statistical test to use here is a chi-square test. Now, we need to control for other variables, and these other variables are maternal age, maternal comorbidity, and then tobacco use, and then parity, prenatal checkup. And then you will note here that maternal age is a quantitative variable, and then so we have here the 2 asterisks, and it says that these 2 asterisks, because the independent variable is quantitative, we'll be using in the univariate analysis a logistic regression. And then we have here, we also calculate for the crude odds ratio. The crude odds ratio is also called the odds ratio in the univariate analysis, and then the adjusted odds ratio, where we calculate the adjusted odds ratio in a multivariate analysis. So you will note that all 5 were consistent. The objective of the study, the operational definition, the sample size calculation, statistical test, and lastly, the dummy table. So when you write your proposal, all of these 5 have to be consistent. That's the end of my lecture, and I hope you're able to understand statistical test.